Lesson 3.3 covers solving systems of equations. An equation of the form ax plus by equals c is a linear equation in either standard or general form. This was covered in a previous lesson. The graph of this equation is always a line. And if you're working with one equation, the solution to that equation is every point on the line. Well, sometimes we're going to use more than one equation at once. We refer to this as a system of equations. And the solution to a system of equations is the point where the two lines intersect. So in the first graph, we've just got the graph of a single linear equation. The second shows us the graph of a system of equations. With a single equation, the solution is every point on that line. With a system of equations, the solution is the point that those two lines have in common. Well, there are many methods to solve systems of equations, and in this lesson we're going to look at two of them. The first method is the graphing method. Usually when you have systems of equations, you'll have two equations and they'll be connected in front with a brace. And that just shows that those two equations go together. So with the graphing method, the first thing I want to do is graph each line. So I'm going to start with 4x equals 12 and y equals 2. These are my special lines, the vertical and horizontal lines, and I know this because each equation has a variable missing. With the 4x equals 12, first divide each side by 4 and we get x equals 3. I'm going to draw my x and y axis. With the x equals 3, since it's x equals, it's a vertical line, and it's passing through 3 on my x-axis. With y equals 2, since I have y equals, it's a horizontal line, and it's passing through 2 on my y-axis. With the vertical and horizontal line, it's very easy to see the point where they cross. The x value is a 3 and the y value is a 2. So my solution is the ordered pair 3, 2. You always give the solutions as ordered pairs unless it's a special case, and we'll look at those examples in a minute. The next example, I have x minus y equals 1 and x plus 2y equals 4. So I want to look at these two equations. If I look at the x minus y equals 1, the easiest way to graph this is with the intercepts. For my x-intercept, I let y be 0. If y is 0, I have x minus 0 equals 1. So basically a shortcut is I could just cover up this y value because I'm replacing it with a 0. If I cover that up, that leaves me with x equals 1. So my x-intercept is 1, 0. For the y-intercept, I let x be 0. If x is 0, cover up your x and you have negative y equals 1. Divide each side by negative 1 and you get y equals negative 1. And if you're comfortable, you can do these in your head. If not, write them out on paper. For the second equation, I have x plus 2y equals 4. The easiest way to graph this is going to be with the intercepts. For my x-intercept, let y be 0. So cover up the y term because 2 times 0 is just going to give me 0. And I end up with x equals 4. Then for the y-intercept, you let x be 0. If x is 0, you'd have 0 plus 2y equals 4. So cover up the x since it's a 0. And I have 2y equals 4. Then divide each side by 2 and I get y equals 2. So if I plot my x and my y intercepts in the first line, I have 1, 0 and 0, negative 1. And I draw that line. Since I'm looking for the point where these two lines cross, make your line extend the full length of the graph. Don't draw it short. Don't barely connect the points. Go ahead and extend it to each end of the graph. Then I have the ordered pairs 4, 0, and 0, 2. So draw your second line through those intercepts. Now I'm looking for the point where they cross. By my graph, it looks like they're crossing at the point 2, 1. So my solution would be 2, 1. The graphing method is good because it gives us a visual picture of what's going on with that system. The problem with the graphing method is sometimes if your lines aren't straight or if you're not as accurate when graphing, you won't be able to tell if that point is exactly 2, 1 or not. So the best way to verify that this is your solution is to plug that ordered pair in. And also you will have some homework questions that will ask, is 2, 1 a solution to this system of equations? So if you ever want to check to see if a point is a solution, you plug it in. So take your first equation, x minus y equals 1, and I'm replacing the x with a 2 and the y with a 1. So I get 2 minus 1 equals 1. And simplify that first side. 2 minus 1 is 1, so I get 1 equals 1. So this solution checks in the first equation. If the solution works in the first equation, you have to check it in the second equation as well. So plug the ordered pair 2, 1 into the second equation. Replace the x with a 2 and the y with a 1. So I end up with 2 plus 2 times 1, which is 2 plus 2, and that gives me 4. And that does equal the 4 on the other side. If the ordered pair works in both equations, it is the solution. So my solution to this system of equations is the ordered pair 2, 1. So let's look at another example. Suppose I have the system x plus y equals negative 5 and 2x minus y equals negative 1. So I want to graph each line. And the easiest way is going to be to use the intercepts. So for my x-intercept, let y be 0. If y is 0, I have x plus 0, or just x, equals negative 5. So my x-intercept is the point negative 5, 0. For the y-intercept, let x be 0. If x is 0, I have 0 plus y, or just y. So cover up the x and you just have y equals negative 5. So the y-intercept is the ordered pair 0, negative 5. Now take 2x minus y equals negative 1. For my x-intercept, let y be 0. If y is 0, cover up this y term because that's just minus 0. And I have 2x equals negative 1. Then if I divide each side by 2, I get x equals negative 1/2. Next, for the y-intercept, let x be 0. So I would have 2 times 0, or just 0. So I'm left with negative y equals negative 1. If I divide each side by negative 1, I get y equals 1. So plot these intercepts. For the first line, I had the points 0, negative 5, and negative 5, 0. For the second line, I had negative 1/2, 0, and 0, 1. So look for the solution. That's the point where the two lines intersect. It looks like my solution is at negative 2, negative 3. So I'm going to list that as a possible solution, negative 2, negative 3. To verify that this is the solution, I want to plug it in and check it. So if I began with this problem and I was asked, is negative 2, negative 3 a solution? I would plug it into both equations and make sure it was true each time. So begin with the x plus y equals negative 5. Let x be negative 2 and y be negative 3. And negative 2 minus 3 is negative 5, so I get negative 5 is negative 5, and that checks out. In the 2x minus y equals negative 1, let x be negative 2 and let y be negative 3. So I have 2 times negative 2 minus a negative 3 equals negative 1. Well, 2 times negative 2 gives me a negative 4. Minus a negative 3, the double negative changes to a positive 3. And negative 4 plus 3 is negative 1. So this solution checks in both equations. If you were asked if this was a solution and it did not check in one of the equations, the answer would have been no. Well, let's look at the next example. Just to save a little time, I've already listed the intercepts and I've graphed the lines. For practice, you might want to go back and do this on your own later. But let's say I have the 2x minus 2y equals 10 and the x minus y equals 6. This system graphed as parallel lines. Well, if you remember, the solution to a system of equations is the point where the two lines cross. Well, these two lines, since they're parallel, they will never cross. So if you ever get parallel lines, because they won't cross, your solution is no solution. In the next example, I have 2x minus 2y equals 10 and x minus y equals 5. The 2x minus 2y equals 10 gave me the x-intercept of 5, 0, and the y-intercept of 0, negative 5. The x minus y equals 5 also gave me an x-intercept of 5, 0, and a y-intercept of 0, negative 5. So when I graphed these two lines, they were actually the same line. Well, if the solution is the point where the two lines cross, these two lines are crossing at every point on that line because they're the same. So whenever you have the two equations that graph as the same line, I want you to write the solution is every point on the line, and then you list either one of these equations. You can list the first one, the 2x minus 2y equals 10, like I have, or you could have written x minus y equals 5. Since those two equations graph the same line, they're equal. They're the same equation, so it doesn't matter which one you write in your solution. Now, most books are going to use the phrase infinite number of solutions. I want you to use the phrase that I've got in the notes, every point on the line, and give one of the equations. This gives us more information about those solutions. Well, let's look at some terms associated with these, and specifically the three possible outcomes that could happen when graphing a system of equations. First, with our first three examples, the two lines could cross at one point. When this happens, the solution is that point where the two lines cross, and I want you to always write that solution as an ordered pair. We could classify this system as independent and consistent, and we're going to look at these definitions in a minute. Next, the two lines could be parallel. Well, if the solution is where the two lines cross, and we know that parallel lines will never cross, the solution here is no solution. Whenever your system consists of parallel lines and the answer is no solution, write out the phrase no solution. This system is independent and inconsistent. And in the final case, the two lines could be the same. Well, this time the solution is every point on that line. And if you're given the solution, you state one of the lines. This system is dependent and consistent. Well, let's look at the definitions for independent, dependent, consistent, and inconsistent. For an independent system, the two equations will graph as distinct or separate lines. If you have two separate lines or two different lines in your system, that system is independent. With a dependent system, the two equations are actually the same line. So if you have two equations that graph as the same line, that system is dependent. With a system that's consistent, that system will have a solution. It'll either have one solution, that one point where the two lines cross, or it could have infinitely many solutions where the solution is every point on the line, and that's the case where they're dependent. But if the system has at least one solution, we say that it's consistent. If the system has no solution, we say it's inconsistent. So an inconsistent system is a system that does not have a solution. Well, as I mentioned before, I like the graphing method because it gives us a picture of what's going on with the system. But let's look at some disadvantages. First, there's just simply too much room for human error. If you don't draw your lines exactly straight, or if you slant your line just a bit too much, you're not going to get the correct solution. The solution completely depends on your accuracy when drawing these lines. Also, if you don't use graph paper, your scaling, those are the little slash marks that you draw on each axis to represent the numbers, that scaling may not be exactly the same, so that would cause you to not get the correct solution. Also, and probably the biggest reason for me, is fractional answers are too hard to pinpoint. If your answer did not fall directly on a box corner, if it fell in between the lines, it's hard to tell what fraction that is. And then finally, if the solution is extremely large or extremely small, it's going to be hard to graph. So suppose my solution, instead of being a 2, 3, suppose it was a 200 and a 500. I just don't want to have to graph numbers that large. So because of this, we're going to look at a second method to solve the system of equations, and that's the addition-elimination method. So consider this system. I have 2x plus y equals 5 and x minus y equals negative 2. Well, I want to know what would we get if we added these equations together. So if we take the 2x plus y equals 5 and we add the x minus y equals negative 2, well, the 2x plus the x gives me 3x. My positive y and my negative y are going to cancel, and my 5 minus 2 is going to give me a 3. Since my y's canceled, I ended up with an equation with just an x, and I can solve for that x by dividing by 3. So I end up with x equals 1. Well, now that I know the x value, let me take that 1 and plug it into either one of my original equations. I'm just going to use the first one. So I have 2x plus y equals 5. So replace the x with a 1 and I get 2 times 1 plus y equals 5. This gives me 2 plus y equals 5. Now if I subtract 2 from each side, I get that y equals 3. So this gives me the ordered pair 1, 3. but I want to know, is 1, 3 the solution? I just randomly added these equations together and ended up getting the 1, 3. So I want to check to see if this is the solution. If you're ever asked if an ordered pair is the solution, you plug it into both equations. So start with the 2x plus y equals 5. Let x be 1 and let y be 3. And this gives me 2 times 1, which is 2, plus 3 equals 5. And the 2 plus 3 is 5, so I do get that 5 equals 5. So it checked in the first equation. If it checks in the first equation, you have to plug it into the second equation. So take the x minus y equals negative 2 and let x be 1 and y be 3. And 1 minus 3 is negative 2, so this checked in the second equation as well. Since this checked in both equations, I know that is the solution to my system. So my solution was the ordered pair 1, 3. Well, now let's look back at why adding the equations together gave us the answer. We saw the y variables canceled, but ask yourself why. Why did those cancel? And specifically, what do you notice about the coefficients? Well, in the first equation, the coefficient was a positive 1, and in the second equation, the coefficient was a negative 1. These are additive inverses or opposites. When I add opposites, they're going to cancel. So 5 and a negative 5 are opposites. If I add them, I'm going to get a 0. Negative 3 and 3 are opposites. If I add those, I'm going to get a 0. So opposites are just the same number with opposite signs. So if we can get the coefficients of one of the variables, either the x or the y, it doesn't matter. If we can get these to be additive inverses or opposites, they're going to cancel when the equations are added together. So that's going to be our goal. Once one of the variables cancel, then we're left with an equation containing only one variable. The goal of the addition-elimination method is to get the coefficients of one of the variables, either the x's or the y's, to be additive inverses. You want them to be the same number with opposite signs. So let's look at some examples using the addition-elimination method. I have x plus 4y equals 5 and negative 2x minus 5y equals negative 1. I want to look at my x's and look at my y's. I don't automatically have opposites this time like I did before. So just consider the coefficients. With my x's, I have a 1 and a negative 2. And with my y's, I have a 4 and a negative 5. Well, I could take this 1 from my first equation, and if it had been a positive 2 instead of a positive 1, I would have had opposites. Well, I can make that be a positive 2 by multiplying by 2. But I'm going to have to multiply the entire equation by 2. So if I multiply my first equation by 2, I've got to multiply each side by 2. On the first side, I'm going to distribute that 2 and end up with 2x plus 8y equals 10. Now I have the same number with opposite signs as my coefficient for x. The x coefficients are opposites. So I'm going to add these equations together and eliminate those x's. So the first equation, after multiplying by 2, I got 2x plus 8y equals 10. My second equation is negative 2x minus 5y equals negative 1. If I add these, my x's are going to eliminate. 8y minus 5y gives me 3y. And 10 minus 1 gives me 9. So I end up with 3y equals 9. Now I only have a y in my equation. If I divide each side by 3, I end up with y equals 3. Now my solution is going to be an ordered pair x, y. Since I had a y value, I know these equations are crossing at one point. Now I just need to find the x. I'm going to take that y value and plug it into any of my equations. I can use the two original equations, or if I wanted to, I could use the 2x plus 8y equals 10 since it's the same as my first equation. So I'm just going to find my x by using the x plus 4y equals 5. So we just found that y was a 3, so plug a 3 in for the y, and we end up with x plus 4 times 3 equals 5. This gives us x plus 12 equals 5. So now I can solve for my x by subtracting 12, and I get x equals negative 7. Now that I've found x and y, always write your solution as an ordered pair. And you always put x first. So my solution is the ordered pair negative 7, 3. Let's look at the next example. I have 5x minus 2y equals 4 and 2x plus 3y equals 13. If I wanted to eliminate my x's, I have a 5 and a 2. The smallest number that those both divide into is a 10. So I would have to multiply the 5 by 2 and the 2 by 5 to make those 10s. If I want to eliminate the y's, I have a 2 and a 3. The smallest number those divide into is a 6. Since 6 was smaller than the 10, I'm going to choose to eliminate my y's. Another advantage to eliminating my y's is that I already have opposite signs. So with my first equation, to make the 2 become a 6, I'm going to have to multiply each side by 3. With the second equation, to make the 3 become a 6, I'm going to need to multiply each side by 2. So when I do this, I'm going to add the equations to eliminate. So the first equation becomes 15x minus 6y equals 12. The second equation becomes 4x plus 6y equals 26. If I add these, my y's are going to cancel. So add your x's. 15x plus 4x gives me 19x. The y's eliminate, and 12 plus 26 gives me 38. Now that I have 19x equals 38, divide each side by 19 and you get x equals 2. Now that we have x, we need to find y. So plug that x value into either one of your original equations, or you could plug it into the equations that we got after we multiplied. I'm going to use the first equation, 5x minus 2y equals 4. So let x be a 2, so I have 5 times 2 minus 2y equals 4. This gives me 10 minus 2y equals 4. We'll solve for y. I begin by subtracting 10 from each side, so I get negative 2y equals negative 6. And finally, divide each side by negative 2, and you get y equals 3. So my solution is the ordered pair 2, 3. Well, in the next example, I have 2/3 x minus 5/6 y equals 14/3, and 3/2 x minus 2/3 y equals 17/3. So you may ask yourself, what do you not like about this problem? Probably the fractions. You've got the fraction button on your calculator, but still, these would be a lot easier to solve if we didn't have the fractions. So the first step, if you choose, you can multiply by the least common denominator for each equation to remove these fractions. So look at the denominators for the first equation. I have a 3 and a 6. The LCD for that would be a 6. For the second equation, I have a 2 and a 3. The LCD for the second equation would also be a 6. And these don't have to be the same. It was just a coincidence that they were both the same. So I'm going to begin by multiplying the first equation by 6. And if you wish to use the button on your calculator, you can. But 2/3 times 6 gives me a 4. 5/6 times 6 gives me a -5. Basically, the 6 is canceled in that one. And then 14/3 times 6 gives me a 28. So I end up with the equation 4x minus 5y equals 28. This equation is the same as 2/3 x minus 5/6 y equals 14/3. Then if I take my second equation and multiply it by 6, 3/2 times 6 gives me a 9. -2/3 times 6 gives me a -4. And 17/3 times 6 gives me a 34. So I end up with the equation 9x minus 4y equals 34. So I'm going to write these two equations as a system. So I can rewrite my system as 4x minus 5y equals 28 and 9x minus 4y equals 34. Now I want to try to get the numbers in front of either one of the variables to be opposites, the same number with opposite signs. With the 4 and the 9, you ask yourself what's the smallest number that both of these numbers will divide into, and that would be a 36. With the 5 and the 4, the smallest number those would divide into would be a 20. It doesn't matter which one you eliminate. I'm probably going to eliminate the y's just because the 20 is smaller. So I need to make the coefficient of each y to be a 20. I want one to be a positive and the other to be a negative, and it doesn't matter which is which. So let's say I want to make my first y to have a coefficient of positive 20. I multiply the -5 by a -4 to get a positive 20. But I can't just multiply the y term. I've got to multiply the entire equation by -4. Since I wanted my first equation to be a positive 20, I want my second equation to be a -20. Well, it's already negative, so I just need to multiply the 4 by 5 to get 20. But I've got to multiply the entire equation by that 5. So when I multiply these, I get -16x plus 20y equals -112. And then 45x minus 20y equals 170. So if I add these, my y's are going to eliminate. The -16x plus the 45x gives me 29x. And the -112 plus 170 gives me 58. So I have 29x equals 58. If I divide each side by 29, I end up with x equals 2. Now I want to take that 2 and plug it back into any equation. I could go back to the original equations with the fractions, or I could go back to these equations where I eliminated the fractions, and that's what I'm going to do. So to find y, I'm going to use the 4x minus 5y equals 28. You don't always have to go back to the original. I usually go back to the original unless the original equations have fractions. So plug in a 2 for the x, and I end up with 4 times 2 minus 5y equals 28. This gives me 8 minus 5y equals 28. So subtract your 8 from each side and you get negative 5y equals 20. And finally divide each side by negative 5 and you get y equals negative 4. So always write your solution as an ordered pair. My solution is the point 2, negative 4. In the next example, I have 2x plus 6y equals 8 and 3x plus 9y equals 3. So I want to eliminate the variables, so I want opposites for my coefficients. With the x coefficients, I have a 2 and a 3. The smallest number that both of those will divide into is a 6. With the y's, I have a 6 and a 9. The smallest number that both of those will divide into is an 18. Since the 6 is smaller, I'm going to eliminate my x's. So I need to make the coefficients for each x be a 6. I want one to be a positive and the other to be a negative. So if I want the x coefficient in the first equation to be a negative 6, I need to multiply that entire equation by a negative 3. Since I'm putting my negative in the first equation, I want my second equation to have a positive 6. So I need to multiply that equation by 2 to get a positive 6. So when I multiply these, my first equation becomes negative 6x minus 18y equals negative 24. My second equation becomes 6x plus 18y equals 6. So my x's are going to eliminate like I wanted them to. But if you notice this time, my y's also eliminate. When both variables eliminate, I simply put a 0 on that side of the equation. Then for the second side, negative 24 plus 6 is negative 18. So I end up with 0 equals negative 18. The problem is both my variables have eliminated, so I don't have a variable left to solve for. Since these variables canceled, I know I've got a special case, and I'm going to look at the remaining statement to determine which type of special case I have. So let's look at the special cases quickly. Like we said, when the variables cancel, the system of equations is a special case. If the remaining statement is false, then the system is inconsistent. And if you remember, an inconsistent system was one which had no solution. So this means the lines are parallel and the solution is no solution. If the remaining statement is true, the system is dependent. With a dependent system, the two equations graphed as the same line. Well, the two lines are the same, so they're going to cross at every point. The solution is the point where they cross, and if they cross at every point, the solution is every point on that line. So let's go back to our example. We have 0 equals negative 18. That's a false statement. So the solution this time is no solution. Now let's look at the final example. 2x minus 2y equals 10 and x minus y equals 5. Each coefficient in the first equation is a 2 and in the second equation is a 1. So it doesn't matter if I eliminate my x's or my y's. The smallest number that both will divide into is a 2. So let's say I want to eliminate my x's. I've already got my 2 in the first equation, so I need my second coefficient to be a negative 2. So I'm going to multiply the second equation by a negative 2. So when I do this, bring down your first equation, 2x minus 2y equals 10. If I multiply the second equation by negative 2, I get negative 2x plus 2y equals negative 10. So my x's are going to eliminate, but if you notice, my coefficients for the y's are also opposites, so they're going to eliminate as well. On the second side of the equation, I have 10 minus 10, which is also a 0. So I end up with 0 equals 0. Since both variables eliminated, I know it's a special case. Since this is a true statement, this is a dependent system. That means my original equations were actually the same line. If they're the same line and the solution is the point where they cross at every point on that line. So for this class, you're going to state the solution is every point on the line, 2x minus 2y equals 10. You could have also stated every point on the line x minus y equals 5. It doesn't matter which of the equations you choose to write in your final answer.